again, this is basic modeling and analysis. By example. So here we go. This is the simplest example I could think of, nonlinear example. You can have a spring, you can have a load on it, and the material on this force deformation relationship is given there on the top right. Basically elastic with the Young's modulus of 30,000 up until a yield point of 60. After that, it's going to go at 0.1 times V. So after yield, it'll be straight hardening at 3,000. So this is the simplest nonlinear example I could think of. So now I'm going to show you the tickle commands to generate this model. So what's the first command we're going to use? Stand for, okay, stand for, pick and stand for time. So the first command we issue is the model command. Model is basic. NDM is 1, NDF is 1. We got one spatial dimension is 1. There's 1 degree of freedom at the nodes. Okay? So we have to create two nodes. Nodes 1 and nodes 2. They're both at x coordinate 0. We're going to use it, we'll model this with 0 length elements. Okay? So there's no length dimension needed. Everybody all right so far? What am I going to do to node 1? So I'm going to fix node 1. And it's going to be fixed into one direction, the only direction we have. And it's going to be, I'm going to set it to be 1, so it's fixed. 0 would be free. Next, I'm going to create my material. I'm going to use a little bit of, some variable definitions here. I'm going to set Fy to be 60. I'm going to set E to be 30,000. And I'm going to set my hardening ratio B to be 0.1. So I'm just using variables. So then when I issue the command heating axial material, I'm going to use stilo1, which gives me the relationship I want. The tag is going to be 1, and then it's going to be $FY, $E, and $B. The nice thing about using these variables is that you actually get to see what they correspond to. So sometime later, if you forgot, well, what's the arguments for steel? If you've written a script like that, it's actually, I need to, here's where I change E. I don't need to go back to the command manual to figure out which particular argument happens to be E. So variables are useful in actually describing different things. It's also useful for people coming along later. If they're looking for problems in your script, they might want to see what values you use, and they might recognize, well, hey, you've actually flipped E and D kind of thing. So they might see where you've made a mistake. It might be pretty obvious to them. So it's useful for people coming along later to both check your code and for you to understand what exactly you did. So variables are very useful. It makes the thing a lot more descriptive, and I encourage you to use them wherever you can. So after we create the material, now we create an element. 0 length element, tag is 1. It's going to go between nodes 1 and 2. It's going to take material 1, and material 1 is going to act in the x direction, the 1 direction. 0 length can have its own multiple dimensions. So for our example, this is all we want here. So having material 1 and material 1 is acting in the x direction. So after we've created the material and the elements, we go create our time series. I'm going to put P. Set P is, again, P is a variable. We're going to put it inside a load pattern. That load pattern is going to vary linearly with time. Okay? So as we increase time, the load factor coming back from the time series is going to increase accordingly. So when the time is 1, the load factor is going to come back as be 1. When the time is 2, the load factor will come back as 2. So that's what a linear time series does. And then we say we're going to give another load in node 2 is going to have the value P. Next, I construct my static analysis. I'm doing load control. So I construct a plate handler, reverse cutting key for the numbering scheme, convergence test on it. We use the Newton-Raphson algorithm to bring the Newton loops each step. The system we're going to use is going to be a profile symmetric positive definite solver. That's the type of solver we're going to use to solve the equation. The integration scheme, we're going to use load control. And for this particular example, we're going to set the time to the increments of load control to be 0.1 and analyze data. So what 0.1 will do is it will increment sort of the load factor by 0.1 in every step. So the first time we actually do an analysis, the load factor from the time series will actually be at 0.1. So we'll be applying 1/10 of the actual peak. So that's what load control does. I'm going to talk more about load control later this afternoon. So then to issue this full thing where I put a load of 100 on it, I would analyze 10 as the command. And then what we can do is we know what the exact answer is for this solution. We can go calculate it, and then we can go compare if our answer is correct. We can put that in the script. Okay? We're just showing you a bit of tickle now, some expression evaluation where I can calculate the correct answer. Okay? Then we will be able to do, once we're done, we're going to use the node displacement command that Desmond was just showing at node 2. We're going to use that to see if we've actually got the correct answer. Okay? Is everybody happy with the tickle there? Nothing complicated? Showing you what I showed you this morning. We're using the node disk command that Desmond was showing. Look at the node displacement, and then we're just going to compare that with the actual value. So for those following with the examples I've given you, see at the top right is that a.tickle. That's the file that this example is in when you download it. So I go in there and run a.tickle. This is what I get. I'm printing out node 2. There's the displacement. And here's my comparison with the graph. And you'll see I guess I did. Okay, it's not equal, right? I messed up. Okay? So somewhere I do. Is it the model? Was it my theory? Anybody want to guess? So here's the thing. There's nothing wrong with my model, but there's nothing wrong with the theory. The problem is your computer. Your computers cannot represent every single number exactly, nor can they do math exactly. Okay? So this comparison, you see they're close to the most of the digits when they start going off. That's a problem just because our computers cannot do the math exactly. And that comparison script was an exact comparison. I wasn't allowing any leeway for the fact that it could be round up in my numbers. Okay? But the important thing it shows is you don't trust the computer for every answer you get. I could make this example, I could make these, next time I will, I'm going to make these numbers a lot more dramatic, just to show you that, round up will have a serious impact on the results. I do it when I was sort of teaching the social class here at Berkeley. I just show them that, by changing a number a little bit on the computer, you can get a dramatic difference in the output. I can get factors of 2. I can factors actually as big as I want in the output response by changing numbers, just by playing with computer math and knowing how computers represent numbers. But it's something that you really have to know. These computers, they do not do math exactly, nor can they represent every single number. Okay, so next example. So we're taking that previous example which we just did, and then instead of the strength increasing after yield, we're going to decrease. Okay? So instead of beta going positive 0.1, we're going to set it to be negative 0.1. So my slope is going to be this. I'm going to keep the rest of the script exactly the same. Question is, how far am I going to get when I do my load control? Okay, this is what's going to happen. So opensees is going to come out with stuff like this. And this is stuff you have to understand if you can be doing nonlinear analysis. What this is basically saying is because I was using the profile solver, it actually failed because the matrix is no longer symmetric, positive, definite. Okay? So AII is less than 0. That means the diagonal entry in the matrix is less than 0, so it's no longer symmetric, positive, definite. And we're using symmetric, positive, definite solve with profile SPD. So the solver fails, the analysis fails. And you see it doesn't fail at the start, it fails at an iteration where when the domains of load factor is 0.6. Okay? So it fails when that unbalanced load is 50. Okay? See the results coming out from node 2? See this unbalanced load, it's saying it's failed at 50. Now if we look at the model, like, 60 was where we should have got to. Okay, before it failed. Why are we failing at 60? Anybody, any answers? So the 50, we're failing at 50 because this 0.1, very simple number. A computer cannot actually represent 0.1 exactly. Okay? It's going to be plus or minus a little bit. Turns out to be plus a little bit. That plus a little bit means we're going beyond the 60, so we can't get to that point. So all we can get to is the 50, but we're just a little bit too high. You don't see it in terms, you don't see it from your script. They're using 0.1, what's the problem with 0.1? It's a number a computer just cannot represent exactly. So if we change our load control from 0.1 to 0.00999, that will get rid of that error. And they both get us up to 60. Okay, so I make the change. Now here I am, I get up to 60. That is as far as I can go with load control. With load control, I keep increasing the load factor. I keep applying, increasing the load I'm applying with load control. At a certain point, all I can get is 60. I can't go any higher than that. But if I want to push the model further, if I want to see how much further the model goes, I've got to switch to something else. I've got to change my analysis. So what I'm going to do is I'm going to switch now from displacement control, from load control to displacement control. Okay, and instead of increasing the load, basically I'm going to increase the displacement that I'm imposing on my model. So I will follow the curve. I'll get up here and then I'll keep going this way because I'm just increasing the displacement. With load control, I'm trying to increase the force every so much. As I say, at a certain point, I've hit that 60. I can't go any further. I can't get up. There's no way I'm going to get up to 70 with this particular model. So I'm not going to go past 60. So with displacement control, I can actually push the model out further. So that's basically the change I made to go from load control to displacement control, which is changing the integration speed. Okay? So then we do some more, technical stuff. Do one time step. I'm going to do 10 steps, one time, analyze one at every time step. At every time step, I can get out the load factor, and then just put out to the screen what the load factor times P is, and then what the total displacement is. So when I then run this example, which is for the deducting, this is what you're going to see. Okay? So I'm going to say we get to 60 in 2 steps, and then we start going downhill. As you see, we start getting here's this, computer roundout stuff. Computers don't represent the numbers exactly. You're seeing it right there. Okay? Question?
You use the command get time. How exactly is time handled in the static analysis?
Okay, the time in a static, think of it as pseudo time. It's the time series needs a time to give me back the load factor. Okay? So this is basically it's basically the load. If you're doing a linear time series, it's basically the load factor. But I'm going to get to it more this afternoon. What that pseudo time is in the static analysis. But think of it as a load factor. But I'd say I'll delve into it this afternoon. When I'm showing you what the different integration schemes are trying to do. So if he is confused, talk to you about it. Any other questions? Okay, I'm going to do the same example. All I'm going to do here is I'm going to use a different type of element. We're going to use a truss instead of a zero length. That's the only difference in this model to the previous model. So what changes do I have to make? Well, we have to give the truss needs some length. Okay? So I'm going to specify node 2 it to be at 1.0. Instead of a zero length element, we can use the element of the type truss. It takes 1, 2, $A, and 1. Okay? So the arguments for the elements are a little bit, they're a little bit different. Dividing is move the node out 1. So that's the difference between the two scripts. So if you understood the previous script, you understand this script. So we do all the same thing, and hopefully if you compare that to the previous one, you'll see the exact, the answer is identical. Okay? Okay. So here's a little example. Instead of just constantly increasing the load on my at node 2, I'm going to play around a little bit. I'm going to basically pull this thing out, push it back in, and pull it out, push it back in. The students do this a lot, comparing the stuff on when their reaction walls, they're pushing and pulling columns. They want to have a look at how the results compare. This is how you do it in opensees. So the model, again, the model is identical to what we just had. We still got that truss, 2 nodes, boundary condition. We've got an applied load. We construct our static analysis as before. And now in the, instead of analyze 10, we're changing what's going on in the analysis. We're using the for each command that we saw in my slides previous presentation, the basic SQL command. So here's the for each. Basically, we're using 2 variables. We're going to use the variable numerator and du. And then we're going to use these are the values. So the first time we come into this loop, numerator is going to be 10. Delta u is going to be 0.001. The second time we come into this body for each statement, numerator is going to be 20. The delta u is going to be minus 0.001. So the first time we're going to do 10 steps this way, then we're going 20 steps back, and then we're going 10 steps. Okay? That's what we're trying to do here. So 10 one way, 20 the other way, and then 10 back. So theoretically we should be back to 0 displacement. We're done. We use displacement control. We control the displacement at node 2 in the 1 degree of freedom direction. At this point, 0, 1 is a mistake. Hopefully the file will have the correct thing. This here should be the $delta u here. So I'm going to construct the displacement controller every time, so that would be delta u. Okay? Then we want to analyze them here. So we'll analyze the 10. Second time in, I want to analyze 20. Third time in, I want to analyze 10. And then again, we want to get what the load factor is coming out of the model. And then we're going to put out that to the screen. So what this displacement control does is trying to figure out the load factor at every step to give you the displacement increment that we're looking for. We'll talk about more about that this afternoon. So here's the results. As I say, I'm going 10 out to the plus 0.01, which is bringing out to 0.01 displacement. And we're going 20 back to negative 0.01. Okay? And then 10 forward. And here's the load at all the steps. Okay, and you see that 36, that's kind of where we were at earlier on. Okay? If you plot it, that's what it looks like. Any questions? Does everybody understand this little script?
You need to have the integrator and or both of
Yes, you do. You need to, before you can construct a static analysis, it needs to have an integration scheme already defined. All you do, and just any time that you add a new integration scheme, it changes what the current integration scheme is. Okay? So I needed this integrator here just to build this analysis. This didn't have to be for displacement control. This first one doesn't need load control or anything. It's just that when I come here, this now sets the integrator to be this new one. And then when I do the analyze command, it's using that new integration scheme. Okay? So new question. Any other questions? Okay, as we're an earthquake country and pretty much most everybody uses opensees for doing earthquake excitation. Here's an example of how we do a uniform excitation in opensees. So here's my model, very similar to the previous model. The only difference is I'm adding a mass at node 2. And I'm changing material as well. Well, this is an interesting one. So my model, what I'm doing is I'm just going to set some period. And I'm going to let opensees do some calculations to figure out what mass I need to use given the period I want in my model. Okay? So in this case, I don't have a model in mind that says, okay, I know what the period of the structure is. Let's go, give me my model based on the period I want. Okay? Okay, so I'm setting a period, I'm setting some stiffness and some damping ratio, I want 2% damping. I set some constants, gravitational constants and pi. And based on these quantities, I derive what my mass should be of the damping or my material. Then after I figured out what all these derived quantities are going to be based on my input, I'm going to create my model. I'm going to add node 2, I'm going to add a mass, $m, which is based again on what the period should be for the structure. I'm going to create my elastic material. I'm going to create another material which has got the damping in it. The elastic material, this C is for the damping matrix. I'm going to put those two materials in parallel and give it to my truss. Okay, now here's where I'm doing the uniform excitation. I've got three things going on here. We have a procedure, read record.pickle. That is just a procedure which will read a ground motion stored in the peer format, which is .ht2 format. It basically gives a bit of crap about where the record was located, the number of points that are in the file, and the delta T also in the file. So the procedure is in this file. Again, it's in this place you can download. And on this next line here, read record, that's where I'm invoking this procedure. It's defined in the file. Whatever record I set, in this case I'm using El Centro. Let's set my record to be El Centro. So I'm going to use El Centro. The procedure is going to create a data file just containing the data points. And it's going to come back with a variable set for dt and the number of points. Then after I've read in that procedure, I can now create my time series. My time series is going to be type path. The tag for the time series, where the data is stated in this file. Every data point in this file is the delta T is this, which came back from the procedure. And the factor for all the points is $G, which is set over here, 36.4. So after I created my time series, which basically will say, given the time, what the different factors are coming out of this uniform excitation, you then create a pattern. The pattern type is uniform excitation. The tag is 1, it takes time series 1, And then the acceleration is also one. So the time period tag, the direction of the acceleration back is the second one. And then it's taking the acceleration. You can also specify velocity and displacement instead of acceleration. In this case, you have to specify the appropriate vectors. And then we'll do some little cheesy integration to give you, because uniform excitation needs the acceleration, which does some cheesy integration to give you from the displacement to give you the acceleration. So I strongly suggest never using the other options that are there, even though they are there, and always specifying the correct acceleration you want yourself. Don't rely on me to give you the best option. Figure it out yourself. Okay? So now the only difference here between the static is we've seen this traffic one before in that first presentation. We're using Newmark. Gamma 0.5 beta, whatever that's pronounced with. Not sure why I did that. The rest is the same. So what this thing is going to do, it looks complicated. We're going to start out with T is 0, set OK to be 0, set my maximum displacement to be 0, and then it's going to run through this. While OK is equal to 0, I can define the rest of my max time, do one step, get the time, get the displacement, and then check the displacement is greater than the max displacement. If it is greater than the max displacement at every time step, we're just setting the current max displacement equal to whatever that displacement that came back was. And then when I'm done, I put in record, period name, and put out some information. So when I run it, it's that. All I get is that information. But the interesting thing about this script is I've set it up so that I can do other stuff. Like here, for example, I've set my record BL Centro. I could have a little for each statement here. I could be, set records to be something, and then I can have for each record in that list, of which El Centro is just one. So all this code here, it stays the same as my parameter study. Again, I could have this, so this could be coming in from the argument list, each different argument. So instead of just say j.pickle, I could be passing in what period I want, what earthquake I want it to do. There's so much you can do when you do it from this batch level. But to do it, before you do it, you set it up to run once with, say, this period 1 is the motion. And then once you got it running, then you go, okay, well, let me modify it a little bit to, say, take in sort of variable arguments where I'm going to pass in the period. So I won't use the T n equals to 1, I'll use the R to B command. And I won't take, say, the record El Centro. The record will also come from the argument list. So this is set up for that. So again, I don't just run a j.pickle, I might run a j.pickle with a period and the particular motional one. It's you kind of set it up to do that when you're creating your script. Everybody got that? That's the way.
Well, this method of running your analysis one step at a time, is it any slower by giving you the entire record?
Oh yeah, it is. It's a lot slower. The correct thing to have done would be to use a maximum node, an envelope node recorder, recorded the maximum, done the analysis, and then when the analysis was done, I open up that file and then read the line out of the thing to do. So just sort of tying this to the previous example that you want to go second group line. But there are other ways. When you get to a programming language environment, there's just so many ways of doing what you want to do. But to do it, you just have to kind of do it once and then you think about it a little. But you're thinking the right way. It's always about performance. Okay, so here's the next example. We're going beyond zero-length element suppressors. Now we're going on to a real steel building. Well, in this case, we're going to keep it elastic. So here's the model. Again, it's available online. I'm doing a couple of different things from the sort of the basic approach. So we're creating my model basic, NDF is 4 nodes. I'm fixing nodes 1 and 2. I've got 2 geometric transformations. Linear, they're both linear, 1 and 2. I've also got PLW sections.pickle. This is a file containing the W sections of the procedures in there. One of these procedures is to create an elastic beam. You give it the tag, the 2 nodes, and the section you want. What E is, and sort of which geometric transformation. Okay? So this file here contains, this is not a command that's available in opensees, this elastic beam. This is something I've created in a procedure that's inside this file here. Okay, so I'm setting PV 10,000. I'm creating my load pattern. Time series, in this case, is just constant. So I'm going to create a gravity load pattern for these two vertical loads. And I'm going to put those inside one load pattern. And then in the other load pattern, I'm going to put my horizontal load. This H, I'm going to put 1, basically acting at nodes 3 and 4. So what we're doing here is we've got 2 load patterns. With 1 load pattern, we've got a constant time series. So no matter what the time is in the domain, it's always going to come back with the same factor, right? No matter what the time is in the domain, these 2 loads are always going to stay constant. The value is not going to change. But these other loads, because they're in a load factor with this time series which changes, they're going to change as the time of the domain changes. So basically what we're going to do is we're going to keep these vertical loads constant, and I'm going to keep increasing these horizontal loads and push the structure. Okay. So, what I've also done here is I'm showing the analysis. So after I create the vertical loads, I'm just going to do one analysis. Load control 1.0, and this is basically my gravity analysis. Typically what we do with our buildings, our structures, we apply sort of our vertical loads first as a constant of gravity load. We apply it, pre-impose them on the building before we hit it with the earthquake. So here we are, we're doing basically the gravity analysis. But these vertical loads are staying constant and we apply them. After we've done our gravity analysis, we come along and we add our load pattern. And we do displacement control. We do 100 steps. So just to show you, this procedure, elastic beam section, is in this file, PLW sections.pickle. All it's doing is going into this large array. Given this is our index, we're looking at this array for these values here. We get the area IXX from this table, and then we just create our elastic beam column. Here's where we're issuing the fix command. Element elastic beam column. The tag is 2 nodes, A, E, and I, which is just coming straight out of the table. Okay? Again, we've created this procedure to do something we're going to do a lot. If you're doing a lot of steel analysis, you can have a nonlinear beam, W section 2D, which would automatically go to get your things through your fiber discretization, create your materials for you. So you can be clever about how you do things. Use the power of this programming language to make your life a lot easier. And when you're looking at your script later on, this is a lot easier to figure out what this model was from having A, I, and something, those values themselves. Okay? As I say, I could have just issued these commands here with the different A, E, and I's in this previous script. But this just looks a lot more, to me reading it, I can see just exactly what the model was. Okay? So here's the thing, we run it, this is the output we get. It's not very interesting, it's a linear elastic problem. That's just going to go later. Tomorrow I'll show you something else. Well, what I can do is I can change the geometric transformation, okay? So before it was linear geometric transformation on the column. Now I'm going to go to the p-delta transformation, okay? Everything else in the file stays identical. So if they ask anybody what's going to happen to the slopes when I run it. So when we run the example, here's the example with p-delta. Okay, here's the example with the linear. As you see, for this particular problem, the type of transformation has a great impact on what the output response is, even though it's a linear system. Okay. Any questions? Okay, so I'm going to change a little bit. Opensees is not just about beam columns, the line elements, the beams, the trusses, the zero length elements. You've also got continuum elements in here. We're going to hear a great deal about these tomorrow. Professor Arduino is talking about the geotechnical parts of opensees. So I'm just going to, again, we're going to show you from the elastic point of view. So here we are, we're going to model this beam. We're going to use quadrilateral elements. As I say, when we're doing continuum models or any type of models, if we can start using these four statements, actually build a model very quickly. And that's exactly what I'm doing here. So basically, if I want to change the discretization of this mesh, I don't have to issue all the different node commands. Basically, all I have to do is to change my discretization, all I have to do is change the number of X and the number of Y. All I do is change these 2 points here. The discretization is handled in my loops where I'm creating the nodes and I'm creating the elements. Okay? Kind of it's the power of this scripting language that you sort of have to use to really appreciate. So so here's that node command buried inside this for statement. I'm going to create a node, here's the X location, Y location, the X location, Y location, depending on whereabouts I am inside of my for statement. Here's where I'm issuing the element command. Here's the element you haven't seen before, it's the plot element. Element tag takes 4 nodes. The thickness is fabric in place, raster plane, thread, fixed plane, thread. There's a material tag. We've already created an ND material instead of a uniaxial material. ND material is elastic isotropic. These are applying the load pattern. Basically, I wanted the 2 middle nodes. So NX and NY have to be odd for this to work. Get these with replication. So there's another option I could use called the block command. Instead of figuring out where the nodes and elements are, there's a block 2D command. There's also a block 3D command. Here's the command that basically takes all the, the number of X, number of Y, and where the 2 endpoints are. This point and this point, it automatically creates a mesh with the appropriate elements and materials. So to get it to work, here's just the valves all up and down, that's the issue. What's the difference between the 2 files? The file looks a lot shorter, but the result will be the same. So here's the result. This is n.tickle and this is o.tickle, 2 different files. As you see, they give the exact same result. So they're doing the same thing. Okay. Lastly, a 3-dimensional cantilever column. So I'm just going to do elastic model. We need the brick element. Instead of the block 2D command, I'm going to use the block 3D command. We have to specify if it's rectangular, it can be 4 corners. We're actually specifying, in this case, we're actually specifying we're getting 8 at every point. roughly specifying a circle. Okay, this is creating a circular mesh as opposed to a rectangular mesh. That's what these things are here. Again, we issue this valve command to evaluate this. And then when you run it, you'll see this. And you'll actually see the little display at the model, I believe. It's actually in the script, I'm not showing it here. Okay. Now tomorrow, Pedro, our Arduino, is going to go all over the bring commands and the quadrilateral commands. We just want to show you from the last point of view, that they're in OpenSeas and how to use them. We have over 100 different element types, and we're not going to get to every single one. But so the basic ones that most people are familiar with are there in OpenSeas. And hopefully in this presentation, we pretty much showed you the basics. Elastic analysis. Are there any other questions? Questions?
I'm sorry, when you go in your argument, there are structure step by step.
Yes.
The final number. For example, if I post the number 100, now go in your object, I'm sorry.
Right.
How many steps there are to go to this structure?
That depends on your show you over here. These are linear time frames. By default, that slope is 1. This is time. There's an option to go take like dollar time, and you provide some value. If you want 1, you can have this as 2 if you want. And you can change that slope to whatever you want. Okay? What happens with OpenSea, you might come along and whatever the time is in the domain, this is our domain. The domain always keeps track of what the current time is. And a time analysis, that's this equal to the sort of what we think of as the time. And static analysis is kind of the lambda, or the pseudo time. But it's some value. We did load control 0.1, okay? And we need to analyze 10. So this is our, so the first time we come in here, the time of the range is going to be 0.1, okay? We analyze, first time, if we do analyze 1, time equals to 0.1. If we get to load control with 0.1, okay? If I done load control, say I analyze 1 again, so the time now will be 0.6. Okay, it doesn't matter what. So it's ignoring this. For right now, ignore the time step. So if we analyze one at a time, increment by 0.1 every time step, because the issue is 0.1. Okay, if I've done load control with a 1.0, say we got 2.0. The first case time would be equal to 2. Second case time would be equal to 4.0. Okay? So that's how the time changes. It's given directly by the control integrator. So every time we analyze the load changes. What happens then to the load package or the applied to load? They just depend on, say for this is 0.2. And we have a linear time period, see? This was slope was 1, this is this value, this will come back as 0.2. Okay? This is our time. This is our load factor. So we we've got a load pattern in there that is that's linear with the work. If we do 0.1, the load factor that applies to load would be 0.1. We're coming in at 0.2, it would be 0.2. If it comes in at the time is 2, the load factor that's applied to the load is 2. When we come in at 4, the load factor is applied at 4. If we got this is a linear. If we've got a constant, the load factor stays, so whatever this, whatever this is, say this is 3. If the time was 0.1, the factor will come back to 3. If the time was 0.2, it's back. No matter what time, the factor comes back. And then the path ones that we can do is, you specify whatever the time, this is like a path. Whatever the load factor is, whatever the time is, the load factor is totally changing. Okay? So we can actually use the path inside a load pattern to use a multi-support excitation. That would include multi-support excitation. Any other questions?
So for this problem, what if we want to apply the lateral load pressure, and then we apply the gravity?
That's fine, you can do that.
And then my gravity load is no longer constant, continuous, right?
Right.
So how?
Well, the thing, okay, if you apply the, so you want, the thing is you can do it, think about it, so you can do whatever you want.
Just define the time point.
You just define the time, right. So this, like opensees, it doesn't care what you've got in your model. It says, oh, I've got a load pattern. Okay, so it'll say, okay, load pattern, here's the time, go apply yourself. So the load pattern goes, okay, what's the domain? So what's the time of the domain? Okay, give me the load factor from the time series. Now, okay, all you loads, here's the load factor to apply to the elements of the nodes. And then it comes, oh, I've got another load pattern. Okay, well, so it goes through every single load pattern that's basically active at that time when it hits the analyze. So no matter what the time is, you can have as many load patterns in there as you want. You can do with them what you want. You can put load patterns in and then remove load patterns, and then add another load pattern. So the opensees doesn't care. We'll get a little bit into it, I think, this afternoon a bit, on resetting the time back to 0 in the domain when you take one load pattern out and add another load pattern. Because if you, so I got away with it here because it was linear. But if this wasn't linear, when I start here, that first analyze is actually happening at time 2. Because it's already, analyze 1 is already being occurred, so the domain is already at time. With load control 1, and I do analyze 1, the time for the domain is now 1.0. So when I come along here, I add this new load pattern in, and I analyze 100. The first analyze, the time of the domain is incremented by 1. So the first time this thing is applied is the time is 2. Okay? So, as I was saying, you just keep adding and taking out load patterns at any time. It just looks for what, it just loop over the current active load patterns in your model. Any other questions?
Can we apply moving load?
Yes.
Yes,
you can. I will get Michael Scott to talk about it this afternoon. He's done it in 2 ways. I believe he's actually you can do it in Pickle, basically by inside the loop, you basically apply, you basically add the new load pattern every time you do it, in which he's changing where the load is being applied. Either it's an element load, he moves it basically along the element, the point load along the element. But each time step, that load is actually getting changed, and he does that in the script. But there's no reason that he didn't. He might have already just put it into coded it up and put it in the program itself, where the load basically moves along the elements, load along. Because the elements don't have a clue what loads are being applied at any one step. What happens is The domain tells load patterns to go apply themselves. Load patterns get the load factor from the time series, and they say, oh, I've got all these loads, so they'll tell all the loads, okay, go apply yourself, go add yourself to the curve to the element. So the element gets, it starts getting all these messages, okay, here's some more load, here's some more load, here's some more load. That's basically what's happening. But so you can, in the typical script, you can just, remove a load pattern, add a new load pattern, and we can decide your force statement. But I can think in touch with Michael Scott. He's doing some work for the Oregon Transportation Department, in which they wanted moving loads along the bridge. Any other questions? Is lunch here? Yes? Okay.